All right, so let's talk a little bit about the theory on how gases behave. And so it's called the kinetic molecular theory, and what we're looking at here are particles of gas, okay? And in any particular gas sample, you're going to have a large volume, okay, compared to the size of the actual molecule, which is considered negligible. We know that gas molecules are constantly moving around in straight paths unless they hit something. Now, we're going to say that those happen with perfect elastic collision, which means that the energy is completely transferred when they actually hit each other. There's no loss in friction or any of those other things. And therefore, the average kinetic energy, that's kinetic energy average, which is usually indicated with this E sub K, is going to be proportional to the absolute temperature, which is, of course, absolute means in Kelvin. Okay, that's the big thing. All right, that's the big thing takeaway about kinetic molecular theory. It's the temperature that determines the kinetic energy of the sample. And so we have to make a couple of assumptions here because, you know, this is all theory. What we're going to assume is that when the gas molecules are far apart, which they usually are, and even when they're close together, they don't have attractive or repulsive forces. So they're not going to react because they are running into each other, but they're not attracted when they're close together, nor are they repelled. And we also are not going to lose any kinetic energy by the loss of friction. Okay, so when the collisions happen, we're not losing any energy, we're keeping all the energy. And we also have to assume that the gas has some mass and the gas has some volume, okay, but everything in between is an empty space, and the mass and volume are both negligible compared to the empty space of the container. And so, if you'll recall, we looked at how gas pressure is formed, and that comes from running into each other or into the walls, whichever. As they run into each other, pressure is created. Okay, so it's the collisions that cause pressure. And we've also seen that they move in some straight line fashion, okay, pretty fast until they run into something, which then they may change their direction as they run into things. So I want to show you this other gas activity that Dr. Abraham and Dr. Gelder have provided us. And in this case, we have 1 mole, I think, of hydrogen. Oh, no, 1 mole of helium. Oops. Can I write over here? Can't write anywhere. We have 1 mole of helium, and we have the pressure at 1 atmosphere. We have a volume of 22.65 and a temperature at 275. Now, I'm sure you can't see this, but what I want you to do is keep your eye on this. Okay, now that is the average speed in meters per second. Okay, so the average velocity of helium in this sample of gas. Okay, so I want you to pay attention. Okay, this isn't going to change, but I'm going to change some other things. So at this particular pressure, volume, and temperature, we have a certain amount of speed for these helium molecules as they run into, oh, I meant to actually track something here. So as this molecule runs into that, it changed directions. Now it's going to run into the wall, I guess, yes, and something else, and it changed directions. But it's not attracting or repulsing any of these others. It's just in there, and occasionally they accidentally bump into each other, and that causes pressure. All right, now the one that I turned on here, it's now moving the red one, showing you that the one we're tracking has different speeds throughout this reaction as it turns, as it hits things, as it slows down, and it speeds up. as it slows down when it hits something or speeds up when it hits something. But still, nothing about the average speed or average velocity in this sample has changed. Now I want to look at this in terms of volume. Let me change. Well, actually, let's add some more helium. What happened here? Nothing about this average speed changed. Okay? Now the helium, there's a whole lot more helium in here, and so there's a whole lot more activity down here, and sometimes the helium we're tracking goes slow, and sometimes it goes fast compared to the average, but nothing about the actual sample changed just because I changed the number of moles. Now I'm going to change this back for a minute. We'll start where we were a minute ago. And let me put the tracking on here so we can watch something. And again, the helium is a little faster right now than the average, and now it got a little slower than the average. And this time I want to change the pressure. Okay, so now I've changed the pressure of this. I was at 1 atmosphere, now it's at 22.64 or something. But notice, even though the pressure changed, and look what happened, the volume decreased right here, but what happened to the average speed of that helium? Nothing. Okay, it's still going at the same average speed that it was before. Let's reset that, and now I want to look at what happens when we change the temperature. Okay, so now we're back to our original thing. We have our original, 1,069 meters per second that we had to begin with. Let's track something, so we'll put something on here so we can track. Oh, it's going very slowly, see, very slowly right now. So we can track one of these helium particles. But this time, I'm going to change the temperature. I'm going to notice right now, we have this blue line, blue line at 1,069 meters per second. I'm going to increase the temperature, and look what happened to the blue line. The average sped up. Now it's almost 1,290 meters per second. That one helium molecule that was in there we were tracking, sometimes it goes really faster, as this one is, and sometimes we'll find that it gets really, really slow. Oh, there it is, a lot slower. But the average didn't change. The average did change when I changed the temperature. Okay, that's the kinetic molecular theory. The kinetic energy, the average kinetic energy of the sample doesn't change unless you change the temperature. All right, so let's look at some of the pictures in our book so we can kind of use that as our guide here. All right, so in this case, this is a representation of some gas molecule like we've just seen, getting around in the sample, running into other things. It didn't run into the wall here, but it could have. So here is something about Boyle's law, okay? Now, in this case, we're going to increase the pressure. Okay, what happens when we increase the pressure? We push down with more pressure on the exterior, and the volume of the gas gets smaller. Okay, so we remember that volume and pressure are inversely proportional. Why does that happen? Why? Because when these molecules are put into smaller spaces, they run into each other. They collide more often, which causes an increase in pressure. All right? How about Avogadro's law? In Avogadro's law, we're going to add some gas, so we're going to add in, and we get an increase in our volume. Now, it's important to recognize what we're doing here. We are keeping this pressure constant. The pressure in both of these is whatever the pressure of the atmosphere is. All right, so in this case, we have something setting nice and happy with its pressure equal to the pressure of the atmosphere. and then we add some more molecules of gas. And at first, we just add it in there. The pressure of the atmosphere, however, is no longer the pressure of the gas because we added more. They run into each other more because there's more gas molecules in there. And so this doesn't happen right away, but the pressure will restabilize at whatever the pressure of the atmosphere is, and you end up with an increased volume. All right? So even though it says things are held constant at some particular temperature and pressure, that is true, but the reaction has to have time, or the interrelationships have to have time to get back to where the pressure of the atmosphere and the pressure of the gas are the same again. Okay, when we first add that gas, that increases the pressure because there's more of it, but it will equilibrate basically, or come back to a position where the atmosphere of the gas and the atmosphere of the pressure are the same, and now we have an increased volume. Let's see, we also need to think about Charles's law. Charles's law. Now, here we are to temperature, right? Because we know that when the volume increases, well, let me put it this way. When the temperature increases, the volume increases. Now, why does that happen? Holding pressure and the amount constant, of course. Because when you increase the temperature, the molecules get more energy. They run into each other a whole lot harder than they did before, and they also run into each other more often because the temperature is higher. And so eventually, after we increase the temperature, the volume will readjust to where the pressure of the atmosphere is again the pressure of the gas. And in doing that, we've ended up increasing the volume. So let's go back here for just a second. Remember, we've got everything traveling with some average kinetic energy, velocity. I couldn't really find a good kinetic energy thing, so we're just using velocity for right now. But that temperature, at whatever this temperature is, right now we have it set at 400 degrees. We have some specific and non-changing functional velocity. What about at this temperature? Let's add argon. That's different, but so what? Does it matter? Now argon is in here, and we have several helium and some argon. Notice that even though we have more things at a high temperature, the pressure of the atmosphere is whatever the pressure of the atmosphere is, but the helium and the argon, in terms of their average kinetic energy, because the velocity doesn't change, none of that changes. So this is kind of a fun little page to look at, and I'll get that up on the website for you. Come back. Where's my PowerPoint? All right. Now, I know this is a very busy slide, all right, but what we're looking at here is 3 different temperatures, and we're going to prove that the average kinetic energy doesn't change, even though many of these particles are moving at different speeds. So here we are with some gas particle. It's at 273 Kelvin. So the only thing I care about is this purple line that I'm going to make dashed red. All right, so like that little visualization we just saw, we have some molecules. Most of them are moving at this average speed, which is roughly, looking at this chart, about 500 meters per second. All right, but that doesn't mean that there's not a few in here moving at, I don't know, 50. and there might be a few in here at 1,200. All right, so the average speed doesn't change even though individual parts may not be quite the same. Now, I'm going to switch to this other one so we can pay attention to a different graph. So we'll go to the other extreme. We were looking at the purple one. Now let's look at the one with the highest temperature here. So if we increase the temperature, now this is the same number of particles. Okay, same number of particles as we had before. We didn't change the amount or N. All we've done is change the temperature. Now we're increasing our temperature, in this case to 2273. What happens to the kinetic energy or the speed? In this case, well, it's a whole lot faster than it once was. This is about, I don't know, what do you think? Maybe 1,250 meters per second on this scale. Here's 1,000 and here's 2,000. So the average molecule is traveling at 1,250 meters per second. But now we have a whole bunch that could be going way smaller. Remember earlier we might have had, let's even do a comparison here. Earlier we might have had this many at this. Well, this has still some that almost don't go. And here's some that go really, really fast. Now that's just at any particular snapshot time in history, but no matter what, the temperature, the velocity still stays the same. Now, we don't call this velocity. We call it speed in chemistry for purposes of differentiating a few things. But one thing we know is kinetic energy is 1/2 the mass times the volume squared. The velocity squared. So we have a mass. And in this case, what we use is 1/2 mu squared, okay, for our speed instead of the velocity. And so the question is, why does the kinetic energy depend on the temperature? That's what we really want to know. But what we do know is at some specific temperature, the kinetic energy of the entire sample doesn't change. It stays the same. We may have some individuals who go faster and some that go slower, but overall, the total average kinetic energy, EK, is going to be proportional to the temperature. What are we going to do, though? Because we know, remember, we know that there's a mass component in here, where this is going to be 1/2 mu squared, where this stands for mass. And I just told you a minute ago, it doesn't matter what kind of particle we're talking about. We could be talking about helium. We could be talking about a really heavy particle of gas. Okay? The average kinetic energy stays the same no matter what the mass is. So how do we jive this with what we've just talked about? Well, again, it has to do with averaging stuff. Okay, so in this case, we have everything at some specific speed. All right, some specific speed. And we have some number of molecules. In this case, O2, which is pretty heavy, okay, has a relatively low molecular speed. They don't have any numbers on here, so let's just say 100 meters per second for the fun of it. Okay, and then here's H2, which has a molar mass of 2 grams per mole. This is 32 grams per mole. Okay, the oxygen doesn't move nearly as fast, but that mass component keeps it at the average. And then there's this hydrogen. It's very, very light. It moves really fast. Okay, it's got a molecular speed, we'll just say, for fun, of 1,000 meters per second. Okay, but together, in your sample of gas, whatever that temperature is, it has an average kinetic energy. So there is a component of the mass, but we don't care about the mass except under certain circumstances. because no matter what kind of particle you think about in a gas sample, if you increase the pressure, the volume decreases. It doesn't matter whether that's helium or oxygen. All right? No matter what the volume, if you increase the temperature, all of those molecules are going to go at a faster speed. All right? So kinetic molecular theory says that the average kinetic energy is proportional to the temperature. All right, so the only way to change that kinetic energy is to change the temperature. Within the individual sample, things like the mass and the velocity matter to an individual particle, okay, but not to the total sample. Whatever the total sample is, that kinetic energy is related to the temperature. And so we've got one more section to do on this where we're going to talk about this a little bit more and see how that works in action.